Welcome to 9.2 Logarithmic Functions as Inverses. So if you read the instructions, your job was to think about number 1 and see if you could figure that out. I'm going to give you a few hints of more values and see if they help you. So if you want to, you can pause it. But I'm going to tell you that if 64 is the input, 6 is the output, 1/8 is -3, 2 is 1. All right, so using those, see if you can see any patterns at all. So notice it's the input's not in any order at all, really. Neither is the output. So I just picked some numbers that were semi-easy to work with the function. And yeah, so if I were you, I'd pause this, kind of think about it a little bit more, and see if you can figure it out. All right, so I filled in a few more of these, and hopefully you figured it out. But if you take 2 and the output is the exponent, the answer is the x. So if you take a look at it, 2 squared is 4. Right? So y is the exponent, 4 is the answer to that exponent and base. Okay, let's look at another one. 2 to the third, 2 times 2 times 2 is 8, right? So y becomes the exponent there. Let's look at another one. 2 to the fifth equals 32. All right, 2 to the 1, whoa, what am I doing? 2 to the -1 equals 1/2. All right, 2 to the 1/2 equals square root of 2. All right, so let's take a look at these. Which of the outputs were we not able to find? Well, I told you all of them. So see if you can think about what these will be. Just kind of think about that. All right, so if I have 2 to the what, gives me 0. 2 to the what gives me -1. All right, so which of the outputs were we not able to find? Well, so far 0, -1, and 3. Why do you think that is? Why did I not give them to you? Maybe you already have a number written down, maybe not, but what's holding us back on these? One thing though, 2 to any power will never be 0. 2 to any power will not be -1. These are both undefined errors. These are not possible. So there's nothing that will produce those. Not at all, right? Because if you think of the job of an exponent, it's to tell you how many times the base multiplies. So there's no way to have an exponent that tells us, you know what, this base is just going to go away, right? That's not going to happen. The exponent's only job is to tell the base how many times to multiply. And so we'll never get a 0 or a negative number either. Okay? All right, number 4. Riley believes that 24 and 4.585 is a point on the graph of this function. So remember, 2 to the y, 2 to the y equals x. So let's check it. 2 to the 4.585, put that in your calculator. Yep, equals 24. Is she correct? Yes. How do we know? Well, we can put that in our calculator, right? Now that we know what creates this pattern, we can check it if they give us a point like that. All right, how are the outputs 8 and 1/8 related? Well, if you look at them, if you look back at your table on your paper, they're exact opposites, right? 2 to the third gives us 8, and 2 to the -3, 2 to the 3 equals 8, 2 to the -3 equals 1/8. If you remember real quick, Any negative exponent's actually telling you to multiply that many times, but in the denominator or numerator, depending on where the negative exponent begins. But in this case, it's moving it to the denominator. So, very similar, just kind of complete opposites there. All right, Alyssa thinks that the output for 3 would be 1.5. So 3 to the y value, so 3 to the 1 point, sorry, our base is not 3, our base is 2. All right, so remember 2 to the y equals x, as stated above. All right, so 2 to the 1.5 should equal 3. Do we have evidence against this? Yeah, we do. All right, we can put this in our calculator. 2 to the 1.5 does not equal 3. 2 to the 1.5 actually equals 2.828. So we're close, but not quite there. Right, Sarah wants to know what power she can raise 4 to get 64. So she writes that down kind of like we just did, exactly like we just did. How is this similar or different to what we were doing earlier, that mystery function? Well, I would argue that it is similar. So we're still dealing with the same concept, right? But the base is different. Similar except for base. Except for the base, right? So we're working with a base 2. But this specific question wants 4. All right, so let's provide Sarah with a strategy for figuring out what that question mark could be. Well, Sarah, I would say guess and check, right? But another option is actually what we're learning today, a logarithm. So logarithmic functions. I want you to write this, go back to number 2, draw a box, write this down. Logarithms are the inverses of exponential. When you're in inverse, the x and y switches, okay? That's the idea. But, so our y will be our output this time, and we're going to write log to represent logarithm. 2 right here, a little subscript is the base, and then x is the input. So what this is saying is it's saying, hey, here's the base, right? What was the exponent to get x? That's what a log is asking you. So it's saying, hey, the base is 2. What was the exponent? I'm going to put an x there. Sorry, a y there, as we did before, right? What was the exponent to give you 64? Well, it was 6, right? So the answer is the exponent. So that's the point of a log, and this is how you write it. All right, so going down here, provide Sarah with a strategy to figure out what that question mark would be. So one thing she can do is she can say log base 4, okay, will give me 64. What was the exponent? That's one way, and we can actually put that in our calculator. I'll teach you how to do that in a bit. But what I want you to do is just kind of think about it yourself. How many times do we multiply 4? 4 times 4 is 16, right? Times 4, 6 times 4, 24, carry the 2. Yeah, 64. So we know the answer is 3. So base, exponent, what it creates, right? So I'm going to call this the answer. Now, not the answer to this problem because the exponent is the answer. That's what we're trying to do. So if you remember last time that we were here, you had to do these exponential problems. What if you wanted to figure out how long? What if there was a variable there and you want to know, well, I mean, this is after 6 hours, but you didn't know, okay, and you wanted to solve this. Well, you can convert it to a log and put it in your calculator and then solve for that exponent. So this is where this math is coming from. This symbol was created to represent this idea, this inverse of the exponential. All right, so what the heck did we just learn? Well, let's put it down on paper. We just learned that b to the y equals x is exponential form, right? How we're going to model that. And if you need to change to log form, well, whatever that b number is going to go right here as a subscript. Whatever the answer was when you applied the exponent will go right there in the x spot. And then whatever the exponent was will take place of the y. So of course this is logarithmic form. And you can see how they relate. And you can move back and forth between these. So let's look at one down here real quick. The base is 2, right? If we change this to, actually let's first do the answer real quick. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 1, 2, 3, 4, 5. So the answer is 5. That's the answer to log base 2 of 32. Answer is 5. All right, so it says, then write the logarithmic in exponential form. So 2 to the 5th equals 32. Okay, so back up to our notes. Just to reinforce that, that's what we're doing there. So try to put this in your own words, but what I want you to think about is the output of a log is the exponent, right? For the base to create, a certain value, right? So the output of a log is the exponent for that base listed to create the answer. So for example, log base 2 of 4. What was the exponent on 2 to create 4? 2. So base, exponent, answer. All right, so a few things. If you remember, we talked about the number e in the last video. So e is the continual growth rate. So it's a fancy number used to talk about this growth, right? So think of a tree. You don't see it growing, but it is. And e will help us take care of representing that growth in a function because it is exponential over time. So e helps us see that. All right. So just kind of remember that. E is a number, okay? It's like pi where it never ends. So that's why we give it a name, E. All right, so here's the thing. If you see L and an N, that's going to be log base E, that is ln, okay? Log base E. It's so common in science and in finance that they just call it ln if you have log base E. All right, so if you just have a log with no base, right, so no number there in B, then the B is actually 10. So if they don't write it, 10 is also a very common one. If they don't write it, it is 10. Okay? Plain and simple. It's 10. So log of x equals y. So we don't see a base. That's technically b to the y equals, sorry, not b. If you don't see a b, it's 10 to the y equals x. All right. Another thing. Our domain is restricted. We're going to have an asymptote. So our domain is restricted. You cannot plug in negative numbers, all right? So our base will always be positive, and because of that, I mean, like we talked about earlier, these just aren't going to work, okay? So your domain is restricted. You can't put in negatives. Why? Think back here, right? 2 to the what equals 0. 2 to the what is going to give us a negative. An exponent won't ever create a negative number. If we have a negative exponent, remember, if we have a negative exponent, it creates a fraction. So that's why we have that domain restriction. All right, sounds good. So think about these. If you want to pause it and do them first, that'd be great. But log base 5, meaning 5 has an exponent. What is it that creates 5? Well, that's a 1. Okay? 36 has an exponent that creates 6. It's actually 1/2. Okay? A 10 has an exponent that creates 1 over 100. It's going to be -2. E has an exponent that's going to create e to the third. Well, if e to an exponent equals e to the third, then the answer is 3. So, if that's a little bit over your head, let's convert it to exponential form and see if that helps a little. So, base, that thing circled, exponent, the thing I just underlined, equals this right here, right? Great. Okay, so take the base, take the exponent, and that's what it equals, right? What's in the log. All right, take the base, take the exponent, what's in the log. Take the base, right? That's not the base. Okay, take the base, give it an exponent, it equaled that. Yep, e to the third equals e to the third. That's a true statement. That's e. All right, let's move on. Okay, fill in the table of values if you start with 3 to the x. So 3 to the x, and you replace the x with -1, you're going to have 1/3. Again, even though the exponent was negative, it doesn't create negative numbers. So that's why our domain's limited. We're going to have 1, 3, 9, 27. So remember, I'm just putting all these x's in the exponent spot. Let's say we did 4, 2, we get 81. Okay? All right. Now we're going to use the inverse. So 3 had an exponent. We don't know what it was. And then it created x. So 3 had an exponent. 3 had an exponent. It created 1/3. What was the exponent? -1. Okay. 3 had an exponent that created 1. What was it? 0. 3 had an exponent that's supposed to be a question mark that equaled 3. Well, it was 1 then, right? 3 to the 1 equals 3. 3 had an exponent that gave us 9. It's 2. 3 had an exponent. Wow. Sorry. That gave us 81. What was that exponent? Well, seems like it was 4, right? All right. What is the relationship between f of x and g of x? How could someone tell this just by looking at the entries in the table? Well, they're inverses. Okay? The x and the y switch. That's what makes them inverses. So if they didn't know what they're doing, they'd see those x's and y flipping and at least know that they are inverses. Okay? All right, day 1. You have a juicy secret. On the first day, you tell your closest friend. So 2 people know about it. On the second day, both you and one other person, you tell both you and another person. So on day 2, because you told someone and your friend told someone, now 4 people know about it. So every day, each person that knows the secret passes it on to one more person that hasn't heard it before. So hopefully, as you notice, we are just doubling, right? Multiplying by 2 over and over and over again. So day 1, 2, 3, 4. Day 4 is 16. All right, so you get the idea. So what we're saying is 2 to the what creates 64. And you can mess around with your calculator, but 2 to the 6 equals 64. So on what day will 64 people have heard the rumor? Day 6. All right, so if we have the population of the city that you live in is 51868. We're multiplying by 2, so we want to know how many days out till we get that many people that know the secret. All right? So log, oh man, this one is going to be really tricky to put in your calculator. So log base 2 of 51868. All right, so we're going to learn real quick about the change of base formula. So you can do this in your calculator. Log button is just right to the left. Look at your calculator. So if you do log of 51868 divided by log of 2. All right? We'll talk about this, but this is called change of base. Put that in your calculator. You get 15.66. All right. So we're going to take a look at some graphs now. But I want you, before we do that, I want you to go to the homework and turn to, we're going to skip those right now, turn to 9.2. What I want you to do is try 1 through 12, and then if you don't feel comfortable on any of those, they're not working out, please email me, and I'll either create a video going over those, or just try to explain it to you through email. So, heads up on that.